Cauchy-Gorsa theorem for simply connected domains. It says that let D be a simply connected domain. D be a simply connected domain and F be an analytic function. F be an analytic function in D, then for any simple closed curve contour, indeed you must write contour, any simple closed contour C in D, the integral of this function over this contour has to be 0. This has to be 0. So the process, it is a very good construction. It's a very method used to prove this theorem. It doesn't depend on anything, but something like this we have done for Cauchy's theorem for triangles also, but here we will not be forming triangles. So the first thing what I'm going to do, what we are going to do here, I'm not, because I cannot write all the details, everything is theoretical, you will get in notes, but you just understand what is going to happen now. You have a domain, and in particular, you have a domain, and what you have to show that in any simple closed contour inside that domain D. Let me take a simple closed curve, this C. You have to show that over this simple closed curve, the integral of this analytic function is 0. So what is the process? What we are going to do first? We are going to divide this region R, which is, I'm going to take C, the boundary, along with the interior part of this contour C. Everything I'm going to take that is within inside of this contour. Then what we are going to do, what you have to do next, you have to note it that what you have to do, you have to draw parallel lines. Let me draw like this. Parallel lines to the real axis, and they must be equidistant. All the lines have to be at equal distance from each other, and with the same distance you have to draw vertical lines. Vertical lines means the lines parallel to the y-axis or the imaginary axis, what you call it. Let's draw the line segments in this way. And what will happen, these lines will divide this region R, which is inside domain D, into squares, and not only squares, because everything is not a square here. Look at this thing, this part. This is not a square. This is not a square here. Oh, it is a big. Let me remove it. I have taken the eraser. Why it's not working? Oh, okay. Let it be. It's removing everything now. Okay. So this is not because some of the region might here. Everything is not a square, but some are squares and some are not squares. Those are squares, we will call them square, and those which are not squares, we will call it a partial square. Let us call it a partial square. Okay, and where it is a complete square, we just call it a square. When I say that it's a square, and then it must be clear to you that it must square. What I mean to say by a square, I mean to say the lines of this figure and including the interior part of this, everything here. So in this way, what we are going to do, we are going to to divide this region into some finite number of square or partial square regions. Let that number be n. Okay? We divide this through square regions. And with this division, and now these squares form the cover of this whole of the region, or which includes the contour C with and its interior. Now next, what we are going to see, first let me call the boundary of this square region to be Cj. Let us denote this boundary to be Cj. Next, we have to first show. Next, we claim that for each epsilon bigger than 0, there is Zj in a certain partial square Zj, where j is equal to 1 to n, such that we have this inequality f of z minus f of zj over z minus zj minus derivative of f at zj, because the function is analytic and the derivative is well defined here, is less than epsilon. We have to claim this thing. I'm not saying that it's happening. We have to establish that yes, it happens. Let us call this inequality as a first. We have to prove this, that for every epsilon there is a point in this square region over which we have this estimate. Now, suppose it is not possible. Yeah, what you suppose? You suppose on the contrary. Suppose on the contrary that there is a square. There is a square. Let me denote that square with I had to give just let me denote it by sigma k. Suppose there is a square sigma k for which there does not exist Zj in sigma k satisfying first. Suppose this doesn't hold. Then what you do? What we are going to do, then we have to do what we have to do. Suppose you have this particular square. I'm not drawing every square right now here. I'm just drawing that particular square for which I have this region. Suppose you have this square here now. Suppose here it is. This one is sigma. Okay, this one. Suppose our this square, you do not have that equality. Then what you do? Then again you have to divide this square into 4 another squares. Consider the midpoints of the sides of this square. Join the opposite sides. Then you divide it into 4 squares. In that way, you get another set of squares. Okay. Then it is divided into further number of squares. Okay. And sigma k is being divided into 4 number of squares. 1, 2, 3, and 4. And what you have assumed that the inequality 1 that we assume here to hold doesn't hold on this square, so it doesn't hold on any of these subsquares. It should not hold on any of these subsquares. But and also each of these subsquare contains the points of the region R, because it is within the region R. Then what you are going to do, we choose one of the subsquares. We might have 3 or 4 subsquares. We choose one of the subsquare. Let it be something what you say. Okay, let it not be. You do not give it sigma naught, because at first stage you have found this square, because I have to find another also. Why to keep sigma k? Let it be sigma naught. And again, let us choose another subsquare, subregion inside this square, which is contained inside sigma naught, over which the inequality doesn't hold. Then again, what you do? Again, you subdivide this subsquare. You again subdivide this subsquare into 4 other squares, and again you get sigma naught will contain sigma 1 and so on, sigma 2, so on up to you will have to repeat this process. So what we want to tell that if in first subdivision we are not able to find a zj which satisfies the inequality that we require, and then in the second, and what we claim here, that at finite number of steps there must exist a sigma k where this inequality must be satisfied. It should not continue further. But further, we suppose there is no end to it. When we say that there is no end to it, that means this process is continuing throughout, but at every step we are finding a square, we are finding a subregion where you do not have that inequality to be satisfied in that particular subregion. Then what you happen, every time you will get a sequence of these squares, and remember we are taking these closed squares, so these are compact sets, and every time what is happening, the diameter of square is becoming 1/4. That means look at this, diameter of sigma naught, sigma 1 is actually, what is the diameter? It is becoming what you say area. Let me call only area. Why I call diameter? The area will also make, because area goes to 0, obviously diameter of a square, but diameter of a square is a length of the diagonal. So length of the diagonal is actually, let me write only area. Area of sigma 1 is actually 1/4 of the area of sigma naught. Area of sigma naught. And in this area, in this way, area of, look at this, sigma k, area of sigma k will be 1/4 to power k of area of sigma naught. And if this process goes indefinitely, the area will approach to 0 as k tends to infinity. If area goes to 0, that means obviously the length of the diagonal of each square, which I am calling here the diameter, this will also go to 0 as k goes to infinity. So now you have hypothesis of the Cantor intersection theorem. What hypothesis you have? You have a nested sequence, sigma naught containing sigma 1, so on. You have a nested sequence of compact sets, and each compact set is a non-empty set, and you have diameter of sigma k going to 0 as k goes to infinity. So what is the conclusion of the Cantor intersection theorem now? Cantor intersection theorem implies, by Cantor's intersection theorem, by Cantor's theorem, I will only refer Cantor's theorem, we have that intersection of these squares k0 to infinity contains a single point z naught. Okay, say it contains z. Now I want to show that this z naught is actually a part of the region R, and region R, remember region R is a closed set, because we have to use. Now let us choose delta to be a positive number, and we have to show that this z naught is an accumulation point of the region R, and to show that this is an accumulation point of region R, what I have to show? I have to show that every neighborhood of this z naught contains points of R other than Z naught. Now then, since sigma k, the diameter of these squares goes to 0, so there exists a certain k sufficiently large such that the diameter of this sigma k becomes less than delta. If this becomes less than delta, then implies that this is a disk and this is Z naught and this is delta. If the diameter is less than delta and sigma naught is also, Z naught belongs to sigma naught, that means the square containing this Z naught, which I have done, which I write sigma k, because corresponding to this k, this square must be lying inside this disk. So this square sigma k lies inside this disk d Z naught delta. But what is this thing? This is a square which it contains. It contains points of R other than Z naught. If it contains the points of R other than Z naught, it implies that this disk about Z naught, this was an arbitrary disk, contains points of R other than Z naught, and this shows that this implies that Z naught is an accumulation point of R, but R is constant. But R is closed. R is closed. Hence, there is a characterization that a set is closed if and only if it contains its accumulation points. Hence, this Z naught is an element of R. So what it means now when we say that Z naught is in R, it implies that F is analytic. F is analytic at Z naught also. अगर F analytic है at Z naught, तो F का डेरिवेटिव भी एग्जिस्ट करेगा. Therefore for जो एप्सिलॉन गिवन है आपके पास, there exists certain delta bigger than 0 such that you'll have this thing Z minus F of Z naught over Z minus Z naught minus derivative of F at Z naught is less than epsilon whenever you have Z minus Z naught less than delta. Is it okay? But then Z naught is in this disk sigma k serves as Zj, and sigma k is entirely lying inside this disk delta d. So this inequality holds. This is the inequality 1 here if it substitutes Z naught to be Zj. But this leads us to contradiction. Why this leads us to contradiction? Because we assumed we reached to the point Z naught with our assumption that this process of subdivision of these squares, it never ends, it continues further. That means it never stops. That means for each sub triangle, for each sub square, you do not have that inequalities one to be satisfied on that subregion. But now what we found here at the end, we found that this subsquare sigma k, but this sigma k, you have this region, this inequality being satisfied. So this leads us to contradiction. Hence, what we must agree now that this region, this process stops. That means that after finite number of steps, you will get the covering of this region R in terms of squares and partial squares, over which the inequality 1 will be satisfied. So till now we are settled here for this estimate. So this claim is done. Now the final attack that we have to do is finally now we have to show that integral f of z, not this way, not this way. Mod of integral fz dz is equal to 0. We have to do this thing now. So we have this claim that over each of the triangle, over each of that square, we have that inequality 1. Now what I'm going to define, I'm going to define a function del zj as f of z minus of zj upon z minus zj minus derivative of f at zj into z not equal to zj, and this is equal to 0, z equal to zj. And I'm going to define this function on this square del j, and this is well defined function there, it's okay, clear there. Then note that because of the inequality that we first proved that, note that modulus of this del zj, this is what we proved, is less than epsilon for each j equals to 1, 2, so on up to n and z in dj. We have this thing. Also, it is quite clear here that also each of del j is continuous. Is continuous at dj. There is no trouble because f is continuous, so you will not have any trouble here. It is a continuous function, and the only troubling point was this point of zj, and at zj you have this to be less than epsilon, so you don't need to worry about that thing here also. So these are continuous functions there. Now with these functions, this is an inequality, I can write fz in the following form. Note that I can write fz as fzj for, note that for, but I have to restrict z in cj, because what is cj? Cj is the boundary of that square that you are considering. I can write it in this way: zj derivative of f at zj plus derivative of f at zj into z plus z minus zj into delta j at zj. You just substitute the value of delta j. You will have z minus zj being cancelled out, and then what you will be left some quantities where you will have that all these terms cancel out. You just have to substitute this value here. It's not, there is nothing new. You just substitute it in place of del zj. You will get f of z here. Is it okay? So now what I have to do, I have to now integrate this expression over cj. Let me integrate it over cj. If I integrate it over, it will be fzj का integral, तो ये constant है, it comes out. It is z. Sorry, you don't have very z here. It is dz over cj minus zj बाहर आएगा, f derivative of zj भी integral cj dz. Plus the another thing is where you have to bring out the constant quantity f derivative of f zj. Z is now a variable, dz cj plus it is cj z minus zj del j of z into dz. Now look at these numbers. Cj is a closed. It is a closed square because it's a boundary of the square or a partial square. So it is a closed contour. So our closed contour, this integral is 0. Value of this integral is also 0. What is it's 0? Value of this integral is also 0. So you don't have, you lost all these terms. What you are left with this one last term only. That means the integral over the Cj of fz dz is equal to, let me take modulus also, and it has to be less than or equal to modulus of Cj. It is mod z minus zj, and it is mod of del j z dz. But this modulus of del jz is less than epsilon, so it has to be less than epsilon integral Cj mod of z minus zj mod of dz. So now what is mod of z minus zj? You are in this part. You have this region here, and you have a certain square. Let me take. You have certain square this, and suppose this is a Cj, and let me take first. This is the Cj. So z minus zj, we are taking it from where we are taking it. We are taking it to be z is on the boundary now. So distance of the points from the boundary is less than this diagonal. What is the diagonal? Diagonal is the maximum length of the points on the square. So if a side of this square is sj and square की सारी sides बराबर हैं, तो length of this diagonal will be root 2 sj by Pythagoras theorem. So that means if length of sides of Cj, which is a square now, is Sj, then mod of Z minus Zj has to be less than or equal to root 2 Sj. So therefore, from above inequality, we have this modulus Cj Fz dz is less than or equal to, you can bring out this is a constant Sj over Cj into mod of dz. But same inequality can hold for the other square also, which is a partial square. If you have this square here, then in that case, what you do, you just consider the full square, of which it is a part. So again, it will be less than this thing. But now this one, this is the length. So length of this is what is the length of this? Length of this has to be the what do you say? The sum of the sides of the square. But the sum of the sides of the square, this is when you have a full square. When you don't have a full square, when you have a case of this partial square, when you have the case of this partial square here, what you can do, you can make a precise estimate. Then you can consider, let me remove this, I'm going to write here as well. So in that case, the length of this part has to be this length. I can this is the length, means its length has to be this side plus this side and the part of this arc. ये जो कंटूर सी का जो पार्ट इसके अंदर है, तो उस पार्ट का जो लेंथ होगा, तो लेट दैट पार्ट ऑफ लेंथ का जो होगा, तो लेट दैट लेंथ, इस पार्ट का जो लेंथ है, उस लेंथ को मैं एल ऑफ सी जे से डिनोट करता हूँ. लेट मी डिनोट इट बाय एल ऑफ सी जे प्लस, so the length will be I can write it to be 4 times sj. What I can say that now the length which is given by this formula, mod of dz, this is the formula of the length, it has to be less than or equal to this thing. ये इससे कभी भी एक्सीड नहीं करेगा. हालांकि मैंने ये बड़ा ही लिखा, मैंने पूरे स्क्वायर का लेंथ भी लिखा प्लस इसमें कुछ और भी रीजन ऐड कर लिया. तो it cannot exceed this, so that means this number has to be less than or equal to root 2 sj into 4sj plus length of cj. Let it be if it is. Now what you have, sj और sj जब multiply होंगे तो it will be sj square and it will be the area of that square, and it will be the area of that square implies that integral over cj mod fz, you don't have mod inside, you are taking mod outside here, mod fz dz is less than or equal to, you have root 2 times 4 and sj into sj, it is what it is, it is again what you say, the sj square, the area of the square, it is 4 root 2, and let the area of that square to be aj plus now what you have next term you have sj being multiplied with there is, you have root 2j times sj times length of that, but again I'm going to look at this thing, this length of cj, which is the length of this part of the contour c, this again, this cannot exceed the length of c, so I'm going to make it length of c. And now since this is a contour, this is a compact, and I can enclose this contour in some bigger square. This is always possible. I can enclose it in a bigger square, and let me fix that square, and let me take side of that big square to be s and its area to be denoted by capital A. Then I can write it to be the, if the side of this bigger square is s, obviously the side of this bigger square is larger than the side of the sides of the each sub-square. So instead of this sj here with the when it is multiplied with this length of cj, I will replace it by capital S, and it has to be less than root 2 times capital S into length of the contour C. And now this implies the total integral over C fz dz, this multiplied times epsilon also, we have epsilon also here because we had this delta j and I have epsilon here also, we have to keep epsilon with it also. Okay, so this is epsilon. Okay, now you have this thing, it is less than or equal to when you take this integral, it becomes summation over j from 1 to n, all those subregions, integral over cj fj dz. See now why I am writing in this way, because I have to draw again because I have a black color I can signify it with. So what I have to integrate this integral over whole of c, but what I am writing here, I'm writing the sum as an integral over all cj's. Cj's include this part also. But remember, when I integrate, I have to integrate in an anti-clockwise direction. When I integrate in this square, let it be something di. I integrate it in this direction. This is the anti-clockwise direction. And when I integrate this over another square next to it, the anti-clockwise direction of it will be like this. And when coming to this common side, our common side, the contribution of the integral will cancel out, because one time you are integrating it in one side and the other time you are integrating in its opposite side, and the signs will change and the integral will cancel out. And similarly at every part of this square you will have this region, the contribution of the integral will be cancelled out, because you are integrating every time on each side of the square, you are integrating 2 times this integral but with opposite directions, so the contribution will cancel out. So the contribution that will remain with you will come only from the parts of the contour C. Will come only from the parts of the contour C. That's why we are able to write this as a sum. Now using the triangle inequality, it gives us less than or equal to, let me write directly this inequality here. It gives less than or equal to, what it is 4 times root 2 sum over aj plus this is the constant quantity being added n times, so it is n times root 2 s times l of c times epsilon. Now this is the sum of the areas of these squares, sum of the areas of these squares inside, and see that the sum of the areas of these smaller squares or partial squares cannot exceed the area of this larger square. So this has to be less than or equal to 4 times root 2 area of the large square A plus n times root 2 s times length of curve C times epsilon. Now see what is there within the brackets. Within the brackets, it is a constant quantity. It's not going to change because the length of the contour is not going to change. The area of the square, larger square, is not going to change. So this is constant quantity. So if we change the epsilon, the term will change, and how it will change? It will go to 0 as epsilon goes to 0. So what it implies? It implies that this means that this integral of fz, because its modulus is 0, hence it is 0. And this is what is the Cauchy-Grosser theorem for simply collected regions. Is it okay? Do you have any questions? Please, now I can take on your questions. बोलिए. नहीं है? So okay then, okay, I don't have any issue. So and there is a remark. What is the remark is that what we did, we just took the simple closed curve. But if you have a domain D, and suppose the curve is not simple closed. If it is not simple closed, what it means, it might be like this, might have self intersections. Then what you are going to do, you are going to consider these curves. You consider first the curve, this one. It is simple and closed. Is it okay? Then you consider another curve. You might have, then you consider another, this one. This is also simple and closed. On this, by Cauchy-Grosser theorem, let it be something C1, let it be C2. Then you consider another curve like this. Then you consider this remaining part from here. And in this way, everything. This is another C3. That means then you can write this C as union of C1 union C2 with certain understanding that what we are doing here. Then our C1, the integral is 0. The integral of fz dz over C will be sum of the integral over C1 fz dz plus integral over C2 fz dz plus integral over C3 fz. Now each of these C1, C2, C3 are simple closed. And so they are simple closed, hence the integral value at each of our integral of f over each of these curves is 0, and so the sum is 0. This is it. So that means the taking this hypothesis that the contour needs to be simple contour is not necessary, even if it is not simple, if it has finite intersection points, and obviously it has finite intersection points. So let's assume that it has, because sometimes maybe the curve is intersecting infinitely, but let's discard that case. But where the curve is intersecting at finitely many points, self-intersection at finitely many points, then the Cauchy-Gorsuch theorem still holds for such type of contours. Okay, so I stop here now. So if you do not have any questions, if you have, please ask.